welcome to the YouTube channel of Coding Club of RVCE. I'm Naman and we're discussing the solutions to the Leetcode Biweekly Contest 125. This is the third problem, count pairs of connectable servers in a weighted tree network. The problem says that we are given an unrooted weighted tree with n vertices representing servers numbered from 0 to n minus 1. So we have a graph of n nodes and array edges in this format. So the array edges is given and we're also given an integer signal speed. Now, for two servers to be connectable, these conditions should be satisfied. So, for A and B to be connectable through C, A should be less than B, A should not be equal to C, and B should not be equal to C. That is to say that all three of these should be distinct. The distance from C to A and the distance from C to B both should be divisible by signal speed. And the final condition is that the path from C to B and the path from C to A should not share any edges. Satisfying these conditions, we have to find all the pairs of servers A and B that are connectable through server C. And finally, we have to return the integer array count of length n, where count I is the number of server pairs that are connectable through the server I. So let's look at the examples. So this is the given graph and the signal speed is 1. Now, what we have to do is for each of these nodes, we have to find the number of valid pairs such that they are connectable through this node. For 0, we can see in the expected output, no valid pair exists. But why? Because all of the other nodes lie on the same branch of 0. So all of them have to share at least one edge, that is this edge. So since one of the conditions is not satisfied, that's why no valid pairs can be formed. For one of the nodes lie on one branch and 4 of the nodes lie on another branch. Since the signal speed is 1, all distances will always be divisible by signal speed. And that's why 0 taken with any of these 4 nodes is a valid pair. So that's why there are 4 valid pairs for the node 1. And that's why the output for 1 is 4. Similarly for 2, 2 of them are here and the other 3 nodes are here. And that's why 2 into 3, that's 6. So the output for 2 is 6. Similarly for 3, 4 and 5. In the next example, this is the given graph and the signal speed is 3. So in the expected output, the only nodes that can have valid pairs connectable through them are 0th and the 6th node. So for 0th node, it has 2 branches. On one branch, we have 6 and 5 and the other branch, all of the other nodes. Since the signal speed is 3, I can see that 0 to 6 is having a distance of 3, which is divisible by signal speed. And 0 to 5 is having a distance of 6, which is divisible by signal speed. Similarly, on this branch, 3 does not have a valid distance, 2 does not have a valid distance, that is 8, and 1 does not have a valid distance, 7. Only 4 has a valid distance of 3, which is divisible by signal speed, and that's why we have only one valid node on this branch. So for 0, the valid pairs that can be connected through 0 are 4 and 6 and 4 and 5, and that's why we have 2 here. Similarly for 6, it has 2 branches. One branch has 5, which has a valid distance of 3, and the other branch has all of the other nodes, but only 0 and 4 among them have a valid distance, that is 3 and 6 respectively. So on one branch we have one node and the other branch we have 2 valid nodes, and that's why the only number of pairs of connectable nodes is 2. So for 0 we have 2 and for 6 we have 2 and all of the other nodes do not have any other valid pairs. Looking at the constraints, so we can see that n has a very small value of 1000. That means that we can go up to n square or n cube complexity, and the edges length is n minus 1. So this means that we have only n minus 1 edges for n vertices. This can be used to conclusively say that no loops can be formed. And since no loops can be formed, it can be concluded that there is always a unique path from one node to another. There cannot be multiple paths from one node to another. You can think about this and try to form some loops, but you'll always arrive at this conclusion. So let's discuss the approach. Let's say we have this graph. and we have a signal speed of 2. So I have to find, considering a single node at a time. So let's say I'm considering this node, and I have to find all the valid pairs that can be connected through this node. So let me fill in the weights of the edges. Let's say this is 1, 1. Okay, so for this branch, this node is having a distance of 1, which is not a valid distance. So we discard this. But this node is having a distance of 2, and it is a valid distance. So we mark this. Similarly, this node is having a distance of 4. So we mark this. This node in this branch is having a distance of 2, which is a valid distance. So we mark this. This node is having a valid distance, but this node is having a distance of 3, which is not divisible, and hence we cross it. Now you have to find the number of connectable pairs, right? For these two nodes to be connected through this node, they have to share this edge. And that's why connecting these two nodes is not a valid pair. But any of these nodes and any of the nodes from other branches can always be connected. I can connect this node with this one, or this one, or this node with this one and this one. That always works because they do not share any edge, as they are in different branches for the connecting node. So what I can do is I can create for each node a temp vector which stores the number of valid nodes in each branch. In this branch, we have 2 valid nodes. In this branch, we have 1 valid node, and this branch, we have 1 valid node. Finally, we can use this temp vector to calculate the number of valid pairs. So we can multiply this 2 with this one and this one. So 2 into 1, 2 into 1. And the other pair is both of these taken together. So 1 into 1. And that would give us a total of 5 valid pairs for this node. Similarly, we can repeat this entire process for all of the other nodes, and that would give us the final answer vector. To code this, we can use the DFS function to traverse each of the branches and create the temp vector. And finally, we can traverse the temp vector to calculate all of these products and sum them to get our answer. That is the whole approach to the question. Let's look at the code. So I've declared the size of the graph, and I've declared the adjacency list and a final answer vector. So I've created the adjacency list, and this is the standard practice in graph questions. Now I have to traverse each node, and for each node, I have to go through all of its branches. So I've taken the node value to be u. For each u, I'm going to each of its branch. I've declared a couple of variables and a vector temp that I discussed about. Now, I'm using DFS to go to each branch, and then in DFS, I'm initializing a count value to be 0. Then the DFS call updates this count value to the number of valid nodes. That is to say that when I'm at this node, I'll call DFS for each of these branches. The DFS for this branch will update the count value to 2. The DFS for this branch will give me 1, and the DFS for this branch will give me 1. So that will fill the temp vector. So this is the DFS call, and I fill the temp vector with count value, and I'm calculating the sum of the count values. I'll explain that in a bit. Finally, when I come out of the loop, I have the temp vector ready with me. Now I traverse the temp vector to calculate the sum that is required. To do that, instead of manually going to each of the pairs, what I can do is take the sum of all of these elements, that's 4, and instead of 2 into 1, 2 into 1, 1 into 1, what I can do is 2 into 4 minus 2, 1 into 4 minus 1, 1 into 4 minus 1. That would give me 4, 3, 3, which is a total of 10. And then I divide it by 2 to get 5. Basically, I've taken all of the pairs twice so that I can easily code it, and then I divide it by 2 to get the actual number of distinct pairs. So that's what I'm doing here. I'm calculating the sum value, and then I'm calculating the current number of pairs. And finally, for the answer vector, I've put in the value of current divided by 2. Now in the DFS function, first of all, if the distance traversed up until now is divisible by signal speed, I'll increment the count value. That is the whole purpose of the DFS function, to update the count value. So I'll increment that, and then I'll recursively call this DFS function for all of the other nodes. I have also kept a check for the parent value and updated the distance in the recursive call. So that would be the whole code of the question. Let's discuss the time and space complexity. So the adjacency list creation would take big of n space, because we have n minus 1 edges. Other than that, we have only a temp vector, which would again take big of n space, since there can be maximum n edges from a particular node. Now, for the space complexity, this loop would take linear time complexity, and I'm traversing the whole graph for each of the nodes. So this is n times, this would take n, and this would again take n. So I can say that this has a time complexity of n square. So the final time complexity of the code comes out to be n square, and space complexity is linear. Let's try to run and sum with this. Yeah, so it's accepted. That's it for this question. See you guys in the next one.
Coding Club.